Hello. Today we are talking about sampling distributions of the sample proportion. First, I want you to remember that a sampling distribution is all possible samples of a certain size, and this helps us determine what we should expect to see in any random sample from a population. They tell us what a typical sample looks like and what a weird sample looks like. We'll start to be able to see how this helps us make predictions and make decisions. Let's say, for example, I want to know what's the favorite ice cream flavor among Spring Valley students. So I give out a survey. I don't want to survey every student because that would be very difficult and very time consuming. So I take a sample of maybe 50 students and see that in my sample 40% favor chocolate. Well, is that the true proportion of students that favor chocolate ice cream? Well, knowing how all possible samples of 50 SVHS students behave will help me see if this sample I collected is typical and representative of the population, or if it might be a bit weird. So let's get to it. Make sure you take down your EQ, pause if you need to. We want to know today what are the 10% condition and the LCC. How can they be applied to estimate a proportion in a sample? So what do we need in order to calculate the probability of a sample having certain characteristics, like 50 randomly selected students preferring chocolate ice cream as their favorite flavor? Well, we need to know properties of the distribution of all possible samples of any 50 randomly selected students. Well, let's imagine this in a binomial situation where we have a binomial random variable x, where x is the number of successes, i.e. the percentage of students that prefer chocolate ice cream in some kind of chance event. Well, remember the formulas for mean that we worked with. That was mu sub x that we denoted, and standard deviation was sigma sub x of a binomial random variable, where mu sub x was going to equal n times p, and then the standard deviation was going to be the square root of n times p times 1 minus p. So since we can classify this as a chance process with success or failure, they like chocolate ice cream as their favorite or they don't, where we have a probability of success p, we can now derive what the characteristics of this center and spread of all possible samples would be. So let's do some derivations. With a sampling distribution, we are considering all possible samples of size n, which means we can transform not just one individual sample, but we're going to transform the random variable x by turning it into a proportion, x divided by n. Remember that a proportion is just the value of that variable takes x divided by the number of individuals n. This is going to give us a proportion, but this is going to be just the proportion in a single sample, so we call that p hat. P hat, remember that's the notation we use for a single sample proportion, and we say that p hat is going to be equal to x divided by n. Now this is going to be really important because this is going to allow us to find the summary statistics by dividing each one by n, because hey, what are we doing here? We are dividing by n. And remember that division is a transformation that affects your measurements of both center and spread. This is an idea from chapter 6 that we've already talked about before. Okay, so now let's go ahead and derive the average sample proportion mu sub p hat. So let's do some derivations. With a sampling distribution, we are considering all possible samples of size n, which means we can transform the random variable x into a proportion by dividing x by n. Remember, a proportion is just simply the value of a variable that is taken divided by the number of individuals, n, in our sample. So that means we have a sample proportion, and the sample proportion notation we use is p hat, and that is going to equal x divided by n. So I could take any possible random sample of students that I get, the number of those students that prefer chocolate as their favorite ice cream flavor, and divide it by my number of samples, my number of individuals that I sample. But again, that's really time consuming to do that for everybody, so we just want to look at the summary statistics, and we can find the summary statistics for what the average sample should look like by dividing each of our summary statistics of the binomial distribution by n. So let's go ahead and do that. So we're going to first take mu sub x and transform it to mu sub p hat. Well, why are we even allowed to do this? Because when we are doing this division, we determined that division is something that affects our measurements of center and spread. This is something that we figured out back in chapter 6. Okay, so mu sub p hat is going to be the same thing as taking mu sub x divided by n. Well, let's stop for a second and just talk real quick about what it is that we are looking at here. Mu sub p hat is saying what's the average sample proportion of students that prefer chocolate ice cream. What should that average look like? What should I expect to see? Well, we take each possible average number of students and divide it by n. We remember that this mu sub x formula from chapter 6 in the beginning of our notes is n times p. And then we take that and we divide it by n. What do you notice here? Pretty simple, straightforward algebra reduction, right? And a numerator and denominator, those cancel each other out, and we are just left with p. Hence, we can say that the average sample proportion, mu sub p hat, is going to equal p. And this is a huge idea, because what is p? How is p different than p hat? This goes back to section 1, 7.1. P represents the population proportion, and something that describes a population is what's known as a parameter. So what that tells us is the mean, or the center, of that sampling distribution of p hat is equal to the parameter p. And we know that if the center of a sampling distribution is equal to the parameter that is trying to estimate, then that statistic that we're using, which in this case is p hat, is unbiased. And from last section, we said that, hey, unbiased estimators are really good. That's exactly what we want to see. That means that the sample is representative of our population. It's behaving like how the population would behave, and that tells us we have a very good statistic. That's exactly what we want to see. Okay, so now let's go ahead and do a similar derivation and see how does the standard deviation stack up. So now we're going to take each possible standard deviation and divide it by n, because we know that the division affects our measurements of spread as well. So remember that this is going to just very simply be sigma sub x divided by n. Well, what was our formula for sigma sub x? This was the square root of n times p times 1 minus p, and that whole thing is being divided by n. And we might think, all right, well, can't I just cancel those out as well, those two n's? And we say, no, we can't, because that square root symbol is kind of throwing things off. So we want to do a little bit of clever manipulation here. Okay, I want to get this inside of a square root symbol, but I can't just throw in a square root symbol. We have to make it so that we're not actually fundamentally changing that denominator. Okay, well, how do I undo square roots? We square things. So if I have a square and a square root, what would happen to those two things? They would cancel each other out. Okay, so that's exactly what we're going to look at, because that's going to divide by the same value, n, but we're just writing it a little bit differently. Now that we've written it a little differently, let's write it one more time, just slightly differently, so that way we can manipulate it further. Okay, now we are considering a big square root symbol, because a radical in both the numerator and denominator, we can just write everything under 1, and this is going to turn into the fraction n times p times 1 minus p, all divided by n squared. Now, since both are inside the radical, we can start to manipulate them. And what do we notice about n's in the numerator and denominator? Well, I have one n in the numerator, but I have two n's in the denominator. Only one of each can cancel out. But that square then goes away. We're left with one n in the numerator, none in the denominator, and now I can rewrite this equation for sigma sub p hat, the standard deviation of the sampling distribution, as the square root of p times 1 minus p all over n. Okay? Now we know what the center is and the spread. In this, what we can take away from this idea is that there's an n sample size in the denominator. And that's going to tell us that if the sample size is increasing, then the denominator gets bigger. And when we divide by a bigger denominator, we get a smaller number. That means the standard deviation gets smaller. So that should be a very helpful tool for us to tell us that, hey, we have a larger sample size gives us less variability in our sampling distribution. And again, that's another thing that's going to give us a good statistic. Okay? So let's go ahead and turn the page and start to try to summarize everything. Alright, so before we actually summarize, we need to look at the standard deviation because it does have one caveat to it. Taking a sample from a population means we are sampling without replacement, and that means that n, the denominator, is going to be changing with every single subsequent individual selected in the sample, right? Every time we take one individual, that denominator is going to decrease just a little bit. Thus, the variation is changing, and we are going to generally lead us to an underestimate of the variability. So this is really kind of a complicated math idea. It's tough to wrap your head around, but here's the shortcut. To get around this, we say that the difference in changing n is negligible, meaning not really that important, so long as our sample is less than 10% of the population size n, and we call this the 10% condition. So the upshot of this, we have to check the 10% condition in order to see that this calculation is okay. We say that sigma sub p hat can be found by this formula only if we say that your sample size n is going to be less than or equal to 10% of n. 10%, same thing as 0.1, same thing as 1 over 10. I don't care how you write it. It doesn't matter. You'll see me write it a bunch of different ways. But basically, we can say that if little n is less than 10% of big N, then we can go ahead and use this calculation. Okay? So now let's summarize how we can use this to examine random samples when we want to look at sample proportions. These conditions that we have to look at are only valid for sample proportions, only for percents, for p hats, right? So make sure we understand that. Now, any random sample will be a member of the sampling distribution of p hat. And after examining characteristics of sampling distributions in section 7.1, we know how random samples tend to behave. We can now identify the center, the spread, and shape of a sampling distribution of p hat. So let's take a simple random sample of size n from a population of size n with a proportion of success p. Then we can describe the sampling distribution of the sample proportion p hat with the following sucks. Well, center, we know that that's going to be looking at the average, so that's mu sub p hat, and we just found before that mu sub p hat is equal to p. For spread, we said we can use this formula, sigma sub p hat, because sigma is standard deviation, that's our measurement of spread, and this formula was found by the square root of p times 1 minus p all over n. As long as the 10% condition is satisfied, you have to check this condition in order to use this formula. It is a requirement. Okay? So we say that n is going to be less than or equal to 1 over 10n. If we check that, then we say, okay, this formula is fine to use. Okay? Now what about shape? How are we supposed to describe the shape? Well, here's the kicker with shape. With a large random sample, the sampling distribution of p hat is approximately normal. Remember, you saw this in your sampling distribution investigation with the Reese's Pieces. As long as the number of successes and failures will be at least 10. So successes and failures must be at least 10. Then we can assume the sample is large enough for normal approximation. Okay? So that is what we call the large counts condition, also known as the LCC, or it's known as the normality condition. So how do we write this out so that we can check this condition with regularity? Well, we say that the number of successes and failures, that's found by taking our sample size times our proportion that were successes, n times p must be greater than 10. And then so this is our successes. this must be checked, this must be a true statement, and then we say that n times 1 minus p, where we take our number of individuals in the sample times our proportion that were failures, not what we wanted to see, must also be greater than or equal to 10. Okay, so then what? Well, let's go ahead and review. We know what center is, we know what spread is, and we know the shape is normal. So now, what is it? We've got a normal sampling distribution, and if things are normally distributed, then that means we can start calculating probabilities using norm CDF and z-scores. So this becomes an amazingly powerful tool. Once we understand how sampling distributions behave, we can start to make predictions about how unusual or typical is any given sample proportion. Huge idea. Okay, and this is really the foundation of all inference that we are going to use for the rest of the semester. All right, so go ahead and take a look at your examples. Make sure you start to summarize, highlight, annotate. We've marked up these notes a ton. I want you to do the same. Have a wonderful day, and I will see you guys next time.